My name is Carsten Benthin, and today I'm going to talk about ray tracing lossy compressed grid primitives. This is joint work with Karthik, Vaidyanathan, and Sven, Woop. In this talk, we address the problem of ray tracing highly complex geometry. For such complex geometry, the memory footprint of its representation is becoming the limiting factor. For example, a standard index triangle mesh requires roughly 30 bytes per triangle without and 36 bytes per triangle with all BVH data. This means a 40 million triangle geometry will require roughly 1.2 GB without and 1.4 GB with BVH data, which is clearly a lot of memory. The question is now whether there is a better and more compact geometry representation, and that's where our new lossy compressed grid approach comes into play. Our lossy compressed grid approach consists of multiple steps, and here's a high-level overview. In the first step, we convert standard triangle or quad meshes into large grids. Then we subdivide these large grids into smaller fixed-size subgrids, which are then compressed in a lossy manner. In the final step, a quantized BVH is built over all subgrids. And during the actual ray tracing phase, we on the fly decompress the subgrid data to obtain the uncompressed vertex data. In the following, we have a closer look at each of these steps. The grid conversion relies on a simple greedy algorithm, which tries to merge as many triangles or quads into a single grid as possible. Once the merging process is done, we rearrange the original vertices according to the new grid layout. The big advantage of grids is that all connectivity information is implicitly expressed, so no connectivity data needs to be stored. In the next step, each grid is then subdivided into smaller, fixed-sized subgrids. We choose a subgrid size of 5 by 5 vertices, which corresponds to 16 quads or 32 triangles. It is worth to mention that during the subgrid subdivision phase, we likely end up with partially filled subgrids at the border of the grid. In this little example here, a 7 by 5 grid is subdivided into two 5 by 5 subgrids, where one of those subgrids is only partially filled. The lossy compression phase starts with a 5 by 5 uncompressed vertex subgrid as input. Next, we create a bilinear patch from the 4 corner vertices of the subgrid. Then we evaluate the bilinear patch at 5 by 5 positions in UV space. These 5 by 5 positions are just a regular grid in UV space. Given the positions on the bilinear patch and the original vertices, we compute the difference vectors or offset vectors between them. Our lossy compression scheme relies on the fact that these difference vectors will typically be very small. That means that these 3D vectors, which take an uncompressed form 12 bytes, can be lossy compressed to 3 bytes using a reduced precision format. We choose a shared exponent format, which takes 3 times 5-bit for the mantissa, 1 time 6-bit for the shared exponent, and 1 time 3-bit for the octant. The good thing is actually that these difference vectors at the corners of the bilinear patch are 0. That means instead of 25, we only need to store 21 of these offset vectors. Also, it's worth to mention that our approach guarantees watertightness because shared edges at the subgrid share the same bilinear vertices and the same offset vectors. So what does a lossy compressed 5 by 5 subgrid actually contain? It contains 4 uncompressed bilinear vertices, which require 48 bytes. Then it contains 21 lossy compressed difference or offset vectors. They require 63 bytes. And the rest, 17 bytes, are taken by auxiliary data, for example, subgrid resolution, object ID, etc. This gives us 128 bytes per subgrid. which corresponds to 4 bytes per triangle, which is a huge reduction compared to the original roughly 30 bytes per triangle for indexed triangle meshes. Now, decompressing a subgrid is pretty straightforward. First of all, we evaluate the bilinear patch at 21 positions. Then we convert for each of these positions from the reduced precision format to the full single precision floating point format. This typically requires only a few bit extract and shift instructions. Then we add these two 3D vectors together, and we also have to move the uncompressed patch vertices to the correct subgrid positions in the corners. This gives us the final decompressed 5x5 vertex subgrid. And it's worth to mention that all these operations can be efficiently done with vector instructions. So retracing these subgrids requires first to build a quantized BVH over them. It's worth to mention that we have no BVH within a subgrid, but only over them. For the actual array subgrid intersection test, we first on the fly decompressed the subgrid data to obtain an uncompressed 5x5 vertex grid. Then we test one array against n triangles in parallel using vector instructions. For a typical CPU architecture, the n equals 8, which means we need 4 iterations to test 32 triangles of the subgrid. Okay, so let's have a quick look at the results that we obtain with our approach. First, we have integrated our approach into the Embry ray tracing kernel library, and we will compare against Embry's own index triangle and grid mesh implementations. We use 3 different example scenes with a complexity varying between 33 and 75 million triangles. And we use a diffuse path tracer to measure performance. So memory consumption is obviously very important. And this chart here shows for the 3 example scenes the memory consumption. On top, we have the triangle meshes from Embry, which require between 1 and almost 3 GB of memory for the 3 example scenes. The Embry grid meshes, which store the data in uncompressed format, require less memory, but our approach with the lossy compressed grids surpasses all of them. Here, our approach requires roughly between 250 and 400 megabytes of data, which is 2 to 7x less memory compared to the competing approaches. Including BVH data, we roughly require just between 5 and 7 bytes per triangle. Besides memory consumption, rendering performance is obviously also very important. This chart here shows relative rendering performance compared to triangle meshes. And you can see that our lossy compressed grid approach, even though it contains some decompression overhead, fares pretty well here. The overhead to rendering is just about 10%. And for one of the bigger scenes, because of the reduced memory footprint and therefore the reduced number of cache misses, TLB misses, etc., we actually surpassed the rendering performance of triangle meshes. In terms of quality or introduced compression error, our approach achieves pretty good results. This chart shows the relative error between the original vertex and its decompressed counterpart in relation to the diagonal of the subgrid's bounding box. Here, the average error that we see for our example scenes is less than 0.3%, and the maximum error over all scenes is less than just 6.3%, which makes spotting any visual difference very hard. In summary, we propose a new watertight lossy compressed geometry representation that requires only 5 to 7 bytes per triangle, including all BVH data. Due to the fast decompression, we observe a similar ray tracing performance versus standard triangle or grid meshes.